Welcome back to ECE 442-542. Next time we meet will be an exam. Hopefully that does not surprise you. The review session for exam number 2 is following this lecture. Hopefully we will still be here. If you're not able to be here, that's okay. I'll continue talking. Exam number 2 material is available on D2L, and I have posted a new Z-transform table on that if that would be of help to you, and in particular what that, I have to remember how many charts I have here, but this is the new table, and essentially what it has is it now has columns associated with Laplace transforms, time domain waveform, the sampled version of that time domain waveform, and the Z transform. And if you're doing a zero order hold equivalent, and if you're asked to find the Z transform of, let's say, for example, the entry in column 4, you don't have to directly take that into the time domain, sample it, and then Z-transform that sampled signal. You can just look at line 4 and say, oh, I have a Z-transform of a term 1 over S plus A. That immediately you can then go to jump to the rightmost column, which is the Z-transform, and say, oh, that's equal to 1 over 1 minus e to the minus A capital T Z inverse. And if you have to express it in terms of Z, powers of Z, you know our sort of strategy. Just multiply by 1, which is Z over Z, and now you have Z over Z minus e to the minus A capital T. And you can immediately then jump from what you might have in the Z transform bracket in your zero order hold equivalent operations and read across the row and immediately put those into the X of Z format that you need. That's the point behind this Laplace Z transform combination table. And we might talk a little bit more about that in the review session, which again is tonight at 7. Today what I want, and the exam is Wednesday at 5:30 to 6:45. Today, I'll just quickly tell you the exam number 2 process, and we will continue with our discussion of design specifications. There you're thinking transient design specifications, settling time, peak time, percent overshoot, how those are related to dominant Z-plane pole locations. In that discussion, let's actually introduce this Nyquist frequency. Maybe people talk about the Nyquist frequency, and we can relate that to what we will be doing in this class in terms of our primary strip in the S-plane. Anything outside of that primary strip, meaning of higher frequencies, actually gets aliased into the primary strip, and it appears like it's aliased like a lower frequency. That's what we mean when we deal with this Nyquist frequency, and we will then go through an example where we might have inconsistent design specifications, and how do we now achieve compatible design specs for 3 simultaneous design specifications in terms of percent overshoot, settling time, and peak time. How do we make that happen? Exam 2 process. First the do's, and then the don'ts, or the yeses and the nos. This is a digital class, so we have zeros and ones. Here's the ones. Here are the yeses. You can bring 2 sheets of notes, so you can bring your original sheet and a second sheet, and it can be front and back, 8.5 inches by 11 inches. You can bring a Z-transform table. The new table is actually 2 pages. Really, the transforms are just on the first page. Transform theorems or properties are on the second page. I guess I'll allow you to bring both pages of that. So you could theoretically have 4 pages that you're dealing with for exam number 2. Is that clear? If you bring the old transform table, you will have 3. Can I get any more involved or convoluted? You can bring a calculator and something to write with. What you can't do or bring is please refrain from talking to yourself or to your neighbor. It's distracting for other people. That is what I heard after exam number 1. So let's just keep focused on your exam and on your 4 or 3 pages. You can't have a textbook since we don't have one anyway. Don't bring one and pretend that I won't recognize it or won't notice it. And course notes. I know these notes are just so comforting, but you have to produce your own set. You have 2 pages to do that, so just put all of your information on the 2 pages of notes. And you cannot have a computer. I knew I was forgetting something. Thank you for the reminder. See, I left myself enough room, and that looks like it's got about 4 or 5 crosses on the T, but that's a T. Any other questions or comments on the process? It shouldn't come as a surprise. You've already been through 1. Now we're going to go through the 2nd, and you'll have a 3rd after spring break. And you can imagine how we're going to learn how to count. I'll just erase that 2 and increase it to 3 sheets of notes. Even though this is binary, we'll be okay. We can, right now we're at 1, 0. In turn, we're at 2. We'll go to 1, 1, and then we may actually have to add another digit for the final. 1, 0, 0 for your pages of notes. Let's get started into the good stuff. Let's talk now about design specifications and dominant pole locations. This may not be explicitly on your exam number 2, but the concepts and the ideas I think are still pertinent to exam number 2, and especially depending on how far we get when we start talking about maybe building up a transfer function that might have these 2 dominant poles that are in play. If I was going to say if I die, maybe you guys can leave, but if my microphone dies, you might tell me. I may not be able to hear it. I may be getting so into this material that I forget that I think I have some extra batteries. We can try to survive the death of the microphone, okay? Hopefully I won't die here, or you'll never forget that maybe throughout your career. Wow, I had an interesting experience as an undergrad. You can tell your industrial interview. I was at a career fair opportunity trying to market you guys, so be gentle on me. I've been interfacing with a bunch of industrial people. No, that's fine. All right, so design specifications and dominant pole locations and this Nyquist frequency and how that plays into this whole process. As a reminder, when we are looking at this S-plane to Z-plane mapping, see, I told you we would tie in exam number 2 material to this lecture today. What did we use? When we want to go from S-plane poles or zeros to Z-plane, what mapping do we use? And hopefully you're just taking it easy because you better know this for Wednesday. You have Z is equal to e to the st. If you're, let's say, doing the pole zero mapping approach, you would have to use this relationship to map your poles and your zeros. Now, we not only have an S and a Z, but we have this new thing. We have a T. This mapping process now introduces a sample period. And that actually puts some new information into this whole process, this S-plane to Z-plane mapping. So let me ask the question, what does T do for us? Or maybe what does it not do for us? Or what does it introduce into this process that maybe we need to keep in mind? Introducing this sample period or sampling a analog waveform or a continuous time waveform actually restricts the number of frequencies we can actually resolve or see. Let me just say that it restricts, by introducing a sample period, it restricts the range of frequencies we can actually resolve or see or distinguish. It's however you want to think about it. 5 might look like 1, for example, depending on how fast we're sampling. A signal that has a frequency of 5 might actually appear or be aliased to look like a frequency of 1 hertz if we've sampled at a particular frequency. And what we want to see that, we have to remember Nyquist. Where Nyquist, if we think of the Nyquist frequency as omega sub n, I might actually write that as omega sub h for the highest frequency that we can actually look at, is actually half the sampling frequency, half the sample frequency. If we're sampling at 30 hertz, or maybe in radians per second, let's say we're sampling at 100 radians per second, we can't resolve anything other than frequencies between 0 and half of 100 radians per second, or 0 and 50 radians per second. That's all we can really distinguish if we've sampled at 100 radians per second. That's what Nyquist is telling us. Let me write that down, and then I'll maybe even show you some pictures. So this omega sub h is, let me get rid of this, say omega sub h is the highest frequency that can be resolved in a sampled waveform. And I'll say that maybe again in different ways. Frequencies higher than that Nyquist frequency, or this omega sub h, which is omega sub s over 2, frequencies higher than omega sub h appear to be between dc and omega sub h. Said another way, frequencies above omega sub h are aliased and appear as frequencies between 0, that's the DC, and omega sub h, which is actually this omega sub s over 2. And I was just having fun before class, and here is an illustration of that via MATLAB. But this light green curve is a sinusoid of 9 hertz. The blue dashed curve is a sinusoid of 1 hertz. If we sample at 10 hertz, we actually are folding the 9 hertz back essentially to where it looks like a 1 hertz waveform. And you can see that if we sample at 10 hertz, we're sampling every 100 milliseconds. We're sampling at 0.1, 0.2. That's these, let's say, stem plots with the circles at the end of the stem. The stem values, which are right on this 1 hertz waveform, that's actually, if we sampled that fast and we underlying had a 9 hertz waveform, we wouldn't be able to tell whether that was a 9 hertz signal or a 1 hertz signal. The 9 hertz looks, it's aliased to look like the 1 hertz. Question? So is this the exact same as propellers? So now this kind of concept, the question was propellers and spinning and now wagon wheels on movies that look like they're going backwards. It's this out of sync behavior because they might be capturing the image at a frequency that's not high enough to give you the resolution that you need. And so now maybe it looks like these wagon wheels are spinning backwards in the, well, it's appropriate. We're in the Southwest. So, you know, when we're watching these Westerns and the movie, we go, wait a minute, that wagon wheel is going backwards. Well, that's a property of aliasing. But this gives you maybe a picture, a waveform picture of what I mean when I say alias. So if we're sampling at 10 hertz, you can't distinguish frequencies above 5. All you'll really be able to see are frequencies between DC, 0, and 5 hertz. Anything higher than that is going to appear, it's going to be aliased to some frequency between 0 and 5. This illustrates how a 9 hertz actually looks just like a 1 hertz. This is just one illustration or one example. But that's what I mean by the Nyquist and aliasing. Let's see how this now plays in to when we start mapping frequencies. Meaning, when I say, oh, we're just walking up the imaginary axis in the S-plane, now if we don't really march off to infinity anymore, we just march off to what location? We can only really walk up as high as half the sampling frequency, and then we're basically done. Anything up higher than that's going to actually get flipped back or aliased back or folded back into 0 to omega sub s over 2. So when I say, oh, you're walking up basically as high as we can go, is determined by how fast we're sampling. Let me say now, what is this Nyquist frequency? And I've just defined it or shown it with a time domain waveform illustration. But now we might call that omega sub n or omega high or omega sub s over 2. Now, one thing that you need to keep in mind when we're talking about this is the idea that negative frequencies will be the same as positive frequencies if they're the same magnitude. And that's because we deal with real coefficients in our transfer functions. The fact that we have real coefficients, and maybe when we get further down we can actually illustrate that, or that might occur during our exam review tonight, but the fact that we have real coefficients in our transfer functions, that means that we have to have, if we have complex poles, they have to appear in conjugate pairs. We can't have one pole at 1/2 plus j 3/4 and not have its twin or buddy at 1/2 minus j 3/4. They have to come in conjugate pairs. Otherwise, we would have complex coefficients in our transfer functions, and we don't want to mess with that. So real coefficients imply that for every frequency, let's say omega sub n, well, let me write it a different way. Let's say for every frequency, if we're walking up the imaginary axis, we might get to a frequency omega sub x. We also have its complex conjugate. Now, let's look at what happens when we start looking or walking around on this S-plane. Suppose now that you've picked an omega sub s. And omega sub s, we've agreed, a rule of thumb is sample 30 times the closed loop bandwidth. So we're sampling much faster than Nyquist. That's okay, and we need to do that for a controls point of view, or from a controls point of view. But the fact that we do have Nyquist does restrict or limit where we are in terms of frequencies that we can see. This is now in the S-plane, so that's j omega sub s if we were up there. We now said that there's a special point which is halfway up there, and anything beyond halfway up there looks like something between 0 dc and j omega sub s over 2. And what we will start to do when you are thinking about what's happening, we really only want to worry about what's going on in the S-plane in this sort of primary strip. Hopefully everything that we are doing is living in this primary strip. Anything beyond that is actually going to get flipped down and look like it's in the primary strip anyway. Let me call this the primary portion, or the primary strip of the complex S-plane. Now, suppose that somebody says, oh, I'm not quite sure what you mean. Suppose somebody says, well, then let's put a pole right there. And it's now 3/4 of the way to omega sub s. We now have a pole three-fourths of the way towards omega sub s. What does that look like when we go through this sampling process? In terms of s, we now have s is equal to j 3/4 omega sub s, but we also can write omega sub s in terms of the sample period. Omega sub s is 2 pi f sub s, but f sub s and capital T are reciprocally related. Omega sub s is just 2 pi over cap T, where cap T is our sample period. And if we cancel a 2 in the numerator and the denominator, then we see that this 3/4 omega sub s we could think of as being at a value of s of 3/2 pi over cap T. So that's our s value when we start with a pole, and we would have its twin down here, but let's just look at one of those poles. Now, let's map that into the z-plane. Again, I'm just reviewing all over the place. We know what the mapping looks like, right? Z is equal to e to the st. But we want to look at this for that particular pole. So we know what the s value is. That's now this j 3/2 pi over t. Well, that's now e to the j forgot my t. This in parentheses was s. Then I hit it with t. The t's cancel, and now my z gets mapped to a point, e to the j, 3 pi over 2. And hopefully you're okay with this where it lives. We started with our, in the s-plane, right on the imaginary axis, our pole. And where would you expect that to live in the z-plane? Right on the unit circle, and if you take the magnitude of z, what's the magnitude of this complex number? That's just 1, isn't it? That's sine squared plus cosine squared, where the arguments of those are 3 pi over 2. And that's sine squared plus cosine squared is 1. Now, if we look at that point in the z-plane, we now have gone all the way around this unit circle (270 degrees), 3 pi over 2. We've gone to pi over 2, then to pi, and then to 3 pi over 2. We're down here at this particular location right there. But we could have just as easily written that as e to the minus j pi over 2. And what did I say about numbers and how they appear? They're going to come in complex conjugate pairs. So if we have a pole at minus pi, j pi over 2, we have its twin up here. And so for this z, we also have its conjugate, which is e to the j pi over 2. And what that's saying then is that if we started with a frequency omega of 3/4 omega sub s, which in terms of the sampling period was this 3 pi over 2t, that's also going to appear like this frequency, or what frequency we end up with when we're at an angle of pi over 2, which is then, let's say, an aliased frequency omega sub a of pi over 2t. So even though we start maybe with the actual the continuous time pole at 3/4 omega sub s, it now actually gets aliased to appear like this pi over 2t. And this one, in terms of where we started, this one was, we could write that as j 3 pi over 2t. We now are 1/3 of that way up the imaginary axis, so this is now actually occurring at j pi over 2t in terms of what we see. And if we now started with something over here, then that's going to have the same real part, but it's going to appear within the primary strip if it's in a secondary strip. Anytime we have something in a secondary strip, it's going to actually get folded into, through this folding frequency, or through omega sub s over 2, into the primary strip. So we have to keep that in mind when we're talking about this S-plane and Z-plane mapping. We can't just go all the way up to infinity in terms of frequencies. What's happening right at this Nyquist frequency. Where are we ending up? If we now looked at omega equal to omega sub n, which is this omega sub s over 2, where does that take us? If we go through this mapping transformation, z is equal to e to the st, and now what do we have at omega sub s? Omega sub s, remember, is this 2 pi over cap t. The 2's cancel, and so right at the Nyquist frequency, or the highest frequency that we're ever going to see in terms of our sample period, is just pi over cap t. If we now use that frequency in here, where does that put us? Where is e to the j pi? What's its magnitude? If we thought of this as a polar number, the magnitude of that is 1. What's the angle? The angle is the argument of that j, isn't it? It's pi, or 180 degrees. So we're at a magnitude of 1 at 180 degrees, or we're at -1. So the highest frequency that we're going to be living at maps to -1 in the z-plane. This we could think of as 1 at 180 degrees, or somebody might say 1 at -180. The upshot of this is that the Nyquist frequency is going to define what poles or points in the S-plane actually get mapped into the Z-plane. And if we're in the left-half side of the S-plane, we're inside the unit circle, because they have negative real parts. Our Nyquist provides our primary strip in the S-plane. So you pick a sample period based on your closed loop bandwidth. Let's say I give you that your closed loop bandwidth is going to be 10 radians per second. How fast are you going to sample in radians per second? 30 times the 10. 30 times 10. That's why I picked something kind of easy to multiply. 6 o'clock. Who knows how clear my head is, right? So 30 times 10, I can do that, 300. So you need to be sampling at 300 radians per second, or that's equal to 2 pi over t, and you can solve for your t from that relationship. Now, let's get back to these design constraints. Now that we know sort of this range of locations in the S-plane that we're interested in, we can now start to even more carefully talk about settling time, percent overshoot, and peak time. Now, the one that maybe is not as easy to think about is this time to peak, or these time to peak lines in the Z-plane. Oh, and I did some more playing today. Some of you were asking, I hope this is the right curve. Some of you were asking, how do we find these zeta lines? Well, MATLAB will do it for you if you want it to. So MATLAB, remember the zeta lines, those correspond to a certain percent overshoot. These angle lines are the time to peak. And I've now sketched those. Actually, MATLAB doesn't quite do this, so I had to kind of spend some time. It doesn't do these nice angle lines. It does the zeta lines, and it does natural frequency lines. Oh, let's just have some fun. So if we go in here somewhere, wow, I've got two, never mind. So I actually, nope, that's not what I called it. Hopefully I'm in the right spot. No, I'm not. Oh, that's the problem with doing this live. Oh, get over there. Okay. Now hopefully I'm in the right place. So if I do a Z grid 4, which is something that I tried to write today, typo. So now if I come over here, forgot the S. Z grids 4. I don't know why I called it grids. Well, you'll see in just a minute. Hopefully it'll execute now. Be patient. That's why I called it Z grids. I created all sorts of grids. This is the 10th grid, but this one shows what I just sketched in terms of zeta lines from point 1 to point 9. Point 1 means how much overshoot relative to point 9. Which one has more overshoot? If I located poles on this zeta line of point 1 versus poles on the zeta line of point 9, which ones are going to be more oscillatory or ringing or have more percent overshoot? The point 1. The closer I get to the unit circle, the more oscillatory things are going to be. And the more your heart gets squished, the less ringing you will have. Okay? And what value is nice? Maybe this 0.7. And that's why I went ahead and, oh, which one was it? I did this morning, so I'm amazed that I remembered which figure it was, but it was figure 8. Okay? Oh, a figure 8. That's not quite a figure 8, is it? That's a zeta of 0.7. So if you wanted to now design a system that had poles with a zeta of 0.7, which gives you how much overshoot, this you should maybe start. And these are all rules of thumb. This is for dominant two-pole transfer functions. This is just an approximation, but it gives you some way to get some insight into what's going on. A zeta of 0.7 gives you how much overshoot? Do you remember? 5%. So that's a nice place to be in the z-plane, is living somewhere on that zeta of 0.7 line. Now, if you forget all of this, you could just say, I don't know what he was talking about. Oh, no wonder it's so mixed up. Thought I had 2 of those, so let me just go to 1. No wonder my computer was slow. You could say, let me get a new figure window, and you might say Z grid in MATLAB, and it gives you this. So just Z grid gives you this, which you're going, ooh. And why you might say ooh is because the aspect ratio might not be what you want, meaning the horizontal tick marks might not be the same as the vertical tick marks, and so your angles aren't really true angles. Is that making any sense? So you need to tell MATLAB, square up. Or make your axis equal. So now it has made the aspect ratio on the horizontal the same as the vertical. And now angles here are true angles. And if you're measuring angles with your protractor, then they're correct. If you had the other curve before you equaled the axes, you're going to have problems. And if you just wanted to say, oh, you know what, I need to figure out, or my design specs have now said I need to live between maybe a zeta value of 0.3. Oh, I can't make up my mind. Maybe it's 0.7 or maybe it's 0.9. And let me just say, I'm not worried about the natural frequency. You could actually do a z-grid with arguments of the zeta values and the frequency. And now you might want to make those equal again. Now you can start to think about where you want your poles to be relative to those zeta values of 5%, whatever 0.3 ends up giving you, and 0.9. 0.9 you really don't have any overshoot. But now you might be thinking what kind of poles you have in there, or where you locate your poles in between those dashed lines. So that's a possibility for you to be able to do. Where was I going? I'm trying to get you to remember these different design constraints. So now let's look at, or try to better understand, the angle lines, the time to peak lines in the z-plane. What's our formula for time to peak? And it's not that involved. Do you remember what it was? Pi over omega d, where omega sub d is our vertical distance in the S-plane of our dominant poles. Time to peak is now this pi over omega sub d. Now, if I normalize that by the sample period, if I divide both sides, the left side and the right side, by the sample period, I'm going to now normalize my time to peak in terms of sample periods. Meaning if I now say, well, time to peak over t is going to be equal to pi over omega sub dt. But what did we call omega sub dt? Do you remember? That was this nice angle, or that's how we defined our angle, theta sub d, in the z-plane. Omega sub dt is theta sub d. I'm trying to get us to think about what different values of time to peak correspond to in the z-plane as far as angles. Let's look at a couple different possibilities for this theta sub d, since we can, I think, picture what this angle theta sub d looks like. Suppose that theta sub d is pi over 10 radians. And if you don't think in radians, but you think in degrees, then an angle of 18 degrees. And you can sort of draw that on your z-plane. If theta sub d is pi over 10, or 18 degrees, then the time to peak over t is pi over theta sub d, but theta sub d is just pi over 10. The pi's cancel, the 10 can jump upstairs, and we now see that the time to peak over the sample periods is equal to 10, or the time to peak is 10 sample periods. If you're picking that angle and you need your peak time to be happening in 10 sample periods, then you would make your angle be pi over 10, or 18 degrees. That's where you would locate your poles, on that angle. Then we have to figure out how far in the unit circle we want them to be, but that's another design constraint. Suppose we move that angle to be more shallow. Suppose theta sub d, now instead of pi over 10, suppose theta sub d is now pi over 20. That's now half of 18, or 9 degrees. And now time to peak over the sample period is 20. Or the system now peaks after 20 sample periods, meaning it's now a slower system. It takes 20 periods to reach the peak, and before it took 10, if our sample period t was the same. If we sketch that now, here is now our z-plane. Suppose I say that this is now 18 degrees, and this one is half that, 9 degrees. If I'm moving from 18 to 9, what's happening to my time to peak? Is it getting bigger or smaller? Or in terms of a constraint, have I tightened the constraint or relaxed the constraint if I move from the black line, 18 degrees, down to 9 degrees? So it's maybe, it moves in the opposite way that the angle is moving. Meaning, when I had an angle of 18 degrees, it took me 10 sample periods. So think of a sample period as 1 second. It took me 10 seconds to get to that peak. Now I make the angle shallower. Theta sub d is now 9 degrees. It now takes me 20 seconds to get there, so it's relaxing that peak time constraint. So this red line, meaning if my angle gets smaller in the z-plane, this corresponds to a relax of the time to peak constraint. Meaning if somebody wants to enhance or make your time to peak faster, you need those poles to be on a bigger angle. And that will make your time to peak shorter in terms of sample periods. Now, if we have all of that, let's look at an example. That was the time to peak is a design spec that we hadn't really talked as much about. Let's look at an example where now we have all three design specs in play. And to get started, let's just assume that we've already fixed our sample period. Let's just assume that our sample period is 10 milliseconds. here are the design constraints that I want to try to meet. Suppose that somebody says, okay, I want a settling time of a half a second or 500 milliseconds or less. Suppose they want a percent overshoot of 20% or less. And suppose they want a peak time of a tenth of a second or 100 milliseconds or less. Now, we want to translate those design constraints into two complex conjugate pole pairs that will dominate our behavior. We want to say, okay, if we have these specs, can we now create two poles that if we obtained those as our closed loop poles in our system, we would satisfy these design specifications. You now have time to think, right? We took a little commercial break for those of you at home. Now, let's look at these three constraints, and maybe if we just satisfy all, maybe they all are consistent. Maybe if we just look at them, maybe we'll be lucky and they'll all work. They'll just sing together in harmony. Maybe they'll be consistent. They'll be okay. Do you remember how to do the settling time spec? When I say settling time spec, you see bullseye. You're right on target. Sorry. So our sample period is 10 milliseconds. We now have a T settling of n sub st equaling half a second, or 0.5. And we can now solve for n sub s. N sub s is that half a second divided by t, or half of 100 in terms of sample periods. We're now at 50 sample periods is n sub s. And now that we know n sub s, we can translate that into a circle in the z-plane. We know that the radius of that circle raised to the 50th power for a 1% settling time needs to be 0.01. And this 0.01 has nothing to do with our sample period of 0.01. I'm sorry, maybe that was a poor choice for the sample period. Is that okay? This is not equal to capital T. It's equal to 1%, which is 0.01. We can now take the log of both sides. The base 10 log is easier because of the 0.01. And R is now 10 raised to the minus 2 over 50, or a value of 0.912. This now, 0.912, will give us a half of a second settling time for a sample period of 0.01. If I want 500 milliseconds or less, which way do I want to move that pole? Closer in from that R or beyond that R? Needs to be shrinking, doesn't it? So we need to be at 0.1912 or smaller to meet that design specification. Let's look at the percent overshoot spec. Again, we're hoping that maybe they're all three going to be consistent. Our percent overshoot spec, first we need to find out what our zeta value is. And zeta, we could either have a sketch of that figure, or we could simply plug this equation in where we have the natural log of PO over 100, with PO being 20. So we have natural log squared of 0.2, pi squared plus natural log squared of 0.2 again, and don't forget to take the square root of that whole expression. That's our zeta value, and for a 20% overshoot, that's a zeta value of 0.456. And you might think of that relative to 0.7. 0.7 was the 5%. We can tolerate a bigger percent overshoot, so we're getting a smaller zeta. And this is the amount of smallerness that we have. Now, if we translate this into, well, we could go into MATLAB and try to sketch a curve with a zeta value of 0.456. But maybe it's easier with our drafting tools to just get an angle with this and our radius that we've just calculated. Because this is a heart, it's a 0.45, and we know how far away we are in terms of radius, and so we could find this, maybe the angle associated with this zeta and the R value, and not have to try to draw that heart with the zeta value of 0.456. Remember our parameterized S-plane poles, they're at minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. Z is equal to e to the st. Here's our R value, and this is our theta sub d, which is omega sub d times t. If we now look at R is equal to e to the minus zeta omega sub nt. We can now take the logarithm of both sides, let's say the natural logarithm now, since we have an e in play. We can now solve for omega sub n t in terms of R and zeta, because those are the numbers that we have. We have R and zeta now after these two design constraints. This is now minus natural log of R divided by zeta. And if we plug that expression in there for omega sub nt, we now have a way of writing theta sub d in terms of zetas and r's, and no omega sub n's, and actually no t. Meaning now we can say that theta sub d, which we know is this omega sub nt square root of 1 minus zeta squared, is actually going to be minus ln of r over zeta square root of 1 minus zeta squared. We calculated R from the first design constraint. We calculated zeta from the second. We can now calculate a theta sub d consistent with those two design specs. And so now theta sub d becomes equal to, what did I compute? It's equal to 0.1798 radians with r equal to 0.912 and zeta equal to this 0.456. This angle and this radius and zeta value are for two of the design constraints. Let's see if the third design constraint is consistent with these numbers. Because from the peak time, what does that give us in terms of a line or lines in the z-plane? I made a big deal about settling time giving you a bullseye. Percent overshoot gives you a heart, the zeta. The peak time gives you the angles. So now let's look at the peak time spec and see if our theta sub d is consistent with this. And what would consistent mean? If we wanted a peak time of 1/10 of a second or less, then or less means what way do we need to move for our angle? If our angle is 0.18 radians, do I want it to be bigger or smaller to be consistent? A quicker peak time means a bigger angle, doesn't it? So I'm hoping that this peak time spec gives me a no, I don't. Well, let's see what happens. So time to peak, I'm chasing my tail now. Time to peak is pi over omega sub d. Omega sub d we can write in terms of our time to peak as pi over t sub p. So this is now pi over 0.1. So I guess if I get a bigger angle here, then that zeta and r value won't be sufficient to meet all three design specs. That's another way of trying to say it. If this constraint actually, if this time or design constraint gives me a bigger angle, then my r zeta are not going to satisfy this constraint. Does that make sense? So time to peak is now giving us an omega sub d. Our omega sub s, we might want to compare that with our omega sub d. Our omega sub s is 2 pi over t. How is our sampling frequency, omega sub s, related to our damped frequency? If I took the ratio of omega sub s over omega sub d, it'd be nice if that was 30 or more, right? Or around 30. It's actually 20. We're going to just assume that's okay. So here, this is only 20 times the damped frequency of oscillation. And we're going to just live with that. Theta sub d is omega sub dt. We just calculated omega sub d to be 10 pi. T is 0.01. So that now we have theta sub d is an angle of pi over 10. Or pi divided by 10. Pi is, and now because of the week, you need to know pi to how many significant digits. It's pi week, right? Pi day is Thursday. That only comes around once a year, so we got to milk it for all it's worth. All right, so now we have pi over 10, or 0.314159. Theta sub d is now 0.314159 radians. That's theta sub d. That's bigger than the theta sub d associated with our zeta and r value. So that means we can't satisfy all three with the present condition that they're in. The r and zeta are not going to give us a quick enough response as they presently are, because we need, for the peak time, for that angle to be bigger, we need the peak time, or based on the peak time, we need it to be pi over 10, or 18 degrees, and we're not there with the other two. Therefore, the percent overshoot spec does not yield a fast enough or a small enough time to peak. What if we picked a larger zeta? Which is moving us in the right direction. That's a smaller percent overshoot, but is it going to give us a bigger angle? Suppose we said, what if we took theta sub d with, well, not, let's just say with zeta equal to 0.6 instead of 0.456. And we know what r is. That's the 0.912. This actually ends up being 0.1228, which is even smaller than this. So we're moving in the wrong direction if we try to meet the design specs with making our percent overshoot less. That's going to cause us to slow down instead of speed up, essentially, making our percent overshoot less. So that's not going to work. So a smaller percent overshoot did not seem to help. Which constraint should we tighten? What do we have picture-wise? We have zeta curves like that, and we have angles like this. If we stayed on this 0.456 curve, which is the upper one, let's say, and if we increased our angle, what are we doing to our radius? If we looked at this moving from the lower angle, or the larger angle, what's happening to the radius? On that logarithmic spiral, it's shrinking, isn't it? Our radius is getting smaller. So maybe we can fix zeta, change our angle to what angle we need for the time to peak, and find the radius that will be in the right direction. It will be faster to give us all three design specifications. Is that making sense? So this thought process says maybe we need to reduce r. And the answer is actually yes. So for a fixed zeta, let's say that's this curve right here. As we move from this angle, that direction, we're collapsing our radius. Does everybody see that? The radius is getting smaller. For a fixed zeta, and a decreasing r, theta sub d increases, which is the correct direction that we want to be moving. So now the question is, what value of r should we select? Now, let's remember what theta sub d was. That was this minus ln of r over zeta square root of 1 minus zeta squared. Well, we can sort of group all of these zeta values together. We're going to fix zeta at 0.456. We can fix that. That will just be a number. We know what theta sub d needs to be. That was pi over 10, or the 0.314. That leaves us with one r, or one variable r, to solve for. Meaning, and from this one equation, we can now say, oh, theta sub d is this minus ln of r times the square root of 1 minus zeta squared over zeta. With zeta of 0.456, which was our 20% overshoot, so we're living right on the edge of that constraint. We're not trying to restrict that. Then if we plug in that zeta value in the square brackets, we end up with theta sub d equaling minus ln of r times 1.952. To meet our time pi over 10, we can plug that into the left-hand side and just solve for r. Or we now have minus ln of r is equal to this theta sub d divided by the number associated with zeta, which ends up being 0.1610. We solve that for r, whoops, and r now becomes e to the minus 0.161, which is a little bit less than 0.912. It's now 85% of 1, 0.851. What does that do for our settling time? We've now collapsed our bullseye. Our settling time better be less than what it was. At 0.912, we had a settling time of half of a second. We can now plug that into our formula. We know that r n sub s equals 0.01. We now know what r is. 0.01 is given. That's the 1%. We can solve for n sub s. N sub s is now minus 2 over base 10 log of r, and with r equal to 0.851, this now says 28 samples or 29 samples. Or a settling time in actual seconds is n sub s times t, which is 290 milliseconds versus the 500 milliseconds. We wanted 500 milliseconds or less. We are now settling much more rapidly than we were before, and that's actually the punchline that I tried to get to last time. Where can I find it? Isn't it fun, that's not Gloria, but that apparently is Gloria if you do character recognition. I'm sorry, I just got a kick out of that. But here is now what I plotted last time. This is now for that set of poles with R of 0.85, zeta of 0.456, or an angle of pi over 10. This is the trajectory that we get in discrete time. We have a peak time of percent, and it settles in 300 milliseconds or 290 milliseconds. And so those two poles that we've now found the radius and angle for would satisfy those three design constraints. And you'll need to be doing that for the rest of the semester. We'll pick up there 2 weeks from today. Wednesday is your exam.